Okay, so let's start. Firstly, any questions about any aspect of the class before I go ahead? Pardon me? Can I show slides in the? Oh, the lights in the front. Control here. Okay, I don't know where the controls are. Okay, any other questions? Okay, so one thing I wanted to start out with is that last lecture, this is actually the module on Boolean algebra, and when I was covering this slide, for the max term case, I had said that the three max terms are M0, M6, and M2, and that was incorrect. It's actually, if you recall, when we had discussed the max term definitions, the M0 term is the bottommost row, and it kind of counts up. So in this particular case, with 3 bits, the different max terms are going to be, so this one instead of M, this one instead of being M0 is going to be M of 7, and likewise this one is going to be M of 1, and this one is going to be M of 5. So just wanted to correct that. A couple of students who had pointed that out. So midterms count as M0, M1, M2 from top down, and max term counts kind of the other way. So that's the only thing I wanted to cover on this one. And the TAs are going to go over this material in more depth. So the other module that we had started on, so we were looking at how to design functions systematically, and we had introduced this notion of the normal form. And the basic idea is that we basically write down the minterms corresponding to all the 1 entries and all of them together. So that's the conjunctive normal form, or sum of products, or just plain normal form. So in this example, which corresponded to a function that was outputting logic 1, whenever the input was either had the value 1 or had a value which was a prime number. And in this particular case, the highlighted rows are the one which correspond to the 1, and we kind of end up writing it as an ORing of minterms number 1, 2, 3, 5, 7, 11, and 13. And the sigma basically means that we are doing an OR. So we had covered this last time, and then we can map this thing to a gate by basically first creating every minterm. And if you recall, a minterm is basically an ANDing of a bunch of literals. Some of them may be inverted, some of them may be not inverted. So for example, M1 corresponds to 0, 0, 0, 1. So you see that the D, C, and B are inverted with this bubble, and then A is going through straight away. So what this is implementing is implementing D bar, C bar, B bar, A, So that's minterm number 1. And likewise, the different minterms are correspond to, each one of them corresponds to an AND gate, but with the inputs being inverted or not inverted differently. So different patterns of input appearing here. And then we take all the minterms and we feed them into an OR gate. So that's the sum part. So we have a sum of products, product referring to the AND terms out here. This general approach can apply to any function. So if I give you a different truth table, as in truth table with, again, let's say 4 inputs, but different possible output values, then all I have to do is to take the corresponding minterms and create my logic function out of it. So relatively straightforward to implement, and in fact, in early days of semiconductor industry, there used to be chips that you could buy where what they had was they had all the minterms of, let's say if it was a 4-input chip, it would have all the minterms put into the chip, and they would have a massive OR gate. But at the input of the OR gate, you can optionally connect or disconnect some of the wires. So I could take a subset of minterms and only have them feed into the OR gate and kind of disconnect the other. So you could literally kind of, those chips were capable of implementing any Boolean logic function, as long as the number of input pins was sufficient. So I could create a chip which can implement any 4-input function. And you basically just kind of blow the fuse on some of the wires to disconnect them or close some sort of switch to connect them. There are modern versions of variants of these technologies available. So there's something called field programmable gate arrays. These again are chips where there are a lot of gates and they have wires, but those wires have little switches which you can program in software. So you can have some of the wires be connected, others being open, and by correctly programming those switches, you can create any logic onto that chip, subject again to limitations of pins. So those of you who would take the follow-on digital lab class in years to come, you would get to use those chips. So that's how sort of the material you're learning here, you'll basically be implementing digital logic, and you'll be using those chips where basically, literally you just write, you use software to write hardware onto those chips, and you get the logic functionality. So sum of product is a general way of implementing hardware. Now the problem out here is that it certainly works, but it's not necessarily always very efficient. As you can see out here, I'm using a fair number of minterms, and in fact, if I'm using sum of products, then in the worst case, how many minterms would I need? Anyone? So if I limit you to using only the sum of product forms, okay, how many minterms in the worst case would a function have? And again, 4 inputs. Anyone? So I heard someone say 2 to the power n or 16. Okay, let's think about it. If you have 16 minterms, what would that function? If I have all the 16 minterms present in the normal form of a function, what is that function? Remember, one of the minterms will always be true, right? I mean, there are only 16 possible minterms. So I'm covering all elements. So one of them will always be true, so the output will always be 1. So that's kind of a useless function. I would not even, I'll just hardwire it to 1, right? So my worst case is that actually I have 15 minterms. That's kind of the most complicated case. So depending upon your logic functionality, I can have a lot of minterms, and let's go back to that example. If I had 15 minterms, then they're basically saying out of the 16 possible choices, my function is 1 for 15 of them and is 0 for 1 of them. So my better strategy there might be to first create a function which is 1 for that remaining row and then invert it, right? So I could do it a lot more efficiently there than with this approach. So depending upon your logic, depending upon your function, this approach could be quite inefficient. So since gates directly translate into silicon area, which in turn directly translates into how costly your chips are, so optimizing logic is quite important, particularly when you are a company like Intel and you're designing chips with sort of many, many billions of gates on the same device. So let's see how we can kind of do this thing. So one of the concepts, and we will still remain to with the sum of products, notion is that we'll try to combine minterms. So we're basically going to say that put some minterms, some of the rows, could they be combined into kind of a super row? And so let's see how kind of that works out. So the truth table that we had, I have just rewritten it out here so that I highlighted the rows which are 1, and then I put this otherwise all the other combinations correspond to 0. So again, 1, 2, 3, 5, 7, 11, 13, those minterms I have 1, and the remaining one is 0. And what we'll do is we'll look at a strategy on how we can combine it. So let's look at these two minterms. Minterms number 2 and 3, and they correspond to 0, 0, 1, 0 and 0, 0, 1, 1. They differ only in one bit position, right? So 0, 0, 1, 0, 0, 0, 1, 1. Only in the last one, that is corresponding to A, do they differ. They are the same for the first 3 bits. So what we'll do is we are going to combine them. They differ only in one place. So we'll basically can factor away the A term. We can basically say that minterm number 2 or minterm number 3, that function can be replaced by the function not D, not C, not B. So those two cases can be lumped together into a shorter AND expression. So previously I had 2 AND expressions. The first one which has 4 terms, the second one which has 4 terms, but by combining them and using our Boolean logic properties, we basically eliminate A and we are left with D, C, and B. So where previously I had 2 4-input AND gates, now I have replaced it by 1 3-input AND gate. So I have saved the gate and I have a smaller gate. Do you see any other term that could be combined like this? So any other rows like these where they differ only in one place and therefore I could merge them? So 5 and 7, good. So 0, 1, 0, 1 and 0, 1, 1, 1, they differ in position number B, right? And any others? Which one? 1 and 1, 7. You're saying 1, 7, 5? No. Oh, okay. 1 and 5. Okay, 1 and 5 we can do. Okay, good. So there are many of these possibilities out there. So let's play them out. In this one, firstly, where we had 0, 0, 1, 0 and 0, 0, 1, 1, what we end up with is 0, 0, 1, x. X basically means I don't care. I mean, both the values are true now. So these kind of smaller combined terms, where I now have an AND term where not all the literals are appearing. I have 4 literals A, B, C, D, but in this AND term, only 3 of them are appearing. So we'll call these are called as implicant. And what implicant basically means is that it implies the function is 1. So whenever this is true, the function is 1. So that's why they're called implicant. So implicant, a minterm is an implicant because that's also an AND function, but not all implicants are minterms. Okay, and implicant in general may have fewer terms in the AND function than the number of inputs that my logic has. So minterm is a subset of all possible implicants. So a minterm may or may not be an implicant, but a minterm, sorry, I messed it up. An implicant may or may not be a minterm, but a minterm is both a minterm and an implicant. So this is an error. So not all implicants are minterms, but all minterms are implicants. And sometimes we call them as just minterms, sometimes minterm of a function. Sort of when we say minterm of a function, we are basically saying for that function is that a minterm, that is a function valued 1 at the time. So our simplification strategy would be to combine rows so that we replace AND gates by smaller and fewer AND gates. So we saw 2 and 3, and now you guys helped me with kind of some of the other examples. So we saw 1 and 5 could be combined, 5 and 7 could be combined, and the same strategy could be extended to combine more than 2 minterms also. Maybe we can combine 4 minterms. So we'll see how that plays out. But the way we'll do it is by kind of a geometric representation. And this is very commonly used by the software, which software programs which do this kind of manipulation. So what we do is we represent the function in a multi-dimensional binary space. So essentially, each literal, each input of my function corresponds to a dimension. So in this case, we are looking at a 3-input bit function with 3 inputs. So we are going to represent it by 3 dimensions, A, B, and C. So that's what you see. A going into the slide, so to say, is B, and then vertical one is C. And of course, on each one of these, I have only 2 possible values, 0 and 1. So what I really have is a cube whose edges are of unit length. And my function, my input values correspond to the corners of the cube. So for example, this corner at the origin corresponds to when all the 3 inputs are 0. This one to the right on the horizontal, on the a-axis, corresponds to when a is 1, the other 2 are 0. Likewise, this far corner is when everything is 1, and so on and so forth. I have all the 8 possibilities occurring in this case. And a given function can be viewed as that it is 0 on some of these corners and 1 on some of these corners, right? I mean, the 8 corners represent the 8 rows of the truth table, and I can label the corners as having values 1 or 0, depending upon whether my function has the value 1 or 0. So let's say the function I wanted to implement was a 3-bit prime. Okay, so a 3-bit prime, so I'm going from 0 to 7. So I have 2, 3, 5, and 7. And I guess given that we have been treating 1 also, so it's actually 1 and 1 are prime. So it's going to be 1, 2, 3, 5, 7. So we are going to look at those values. So for this function, I'm going to label the function corresponds to those rows 1, 2, 3, 5, 7. And on the cube, what we'll do is we'll mark those corners which correspond to the minterms of this function. So I have marked those. So for example, this corner corresponds to 1. This corner corresponds to 3. The corner out here where the cursor is the 2. 101 is 5, and 111 is 7. So I have 5 corners of this cube marked as something where the function has a value 1. Now, merging means I'm merging adjacent rows in the truth table. That's or rows which differ only in 1 dimension. Those we could merge. In our cube, that means those are corners which are connected by an edge. So any 2 corners which are connected by an edge differ only in one of value for only one of the variables. So for example, if I look at 101 and 111, which is minterm 5 and minterm 7, they're connected by this edge, and they differ only in the B dimension. Likewise, if I look at 010 and 011, so that's minterm number 2 and minterm number 5, sorry, minterm number 3, they differ only in the A dimension. So because they too are connected by an edge. So our merging strategy basically becomes looking at this cube and seeing whether 2 vertices are connected by an edge. If 2 vertices are connected by an edge, they could be merged because they differ only in one place. So how many merging opportunities do you see for this function? again, I mean, the 5 of the corners, the one with the cyan-colored circle, are the one which belong to the function. And we need to look at what pairs are connected by edges. So, check how many of them are connected by edges. How many pairs? 5? Yeah. Okay. So every edge on this face, since the whole face, all the 4 vertices are covered, so all the 4 edges are candidates, and then we have this edge at the back. So there are 5 possible pairs which could be merged, and they would now correspond to AND gates which would have only 2 inputs. But we could do more, and we'll see how sort of that could be done very shortly. So merge midterms into edges. And so we do this one, and so I'm coloring them with this purplish, pinkish color, and this one at the back. And I represent these edges by replacing the edges represented by one of the positions being an x, corresponding to whichever dimension that edge is in. So for example, if I look at this edge which is connecting 0, 0, 1 and 0, 1, 1, it's different. The middle bit, namely bit B, changes. So we call it 0x1. It's basically saying that this edge, both the points on this edge, the first bit is 0, middle bit could be 0 or 1, and the final bit is 1. And likewise, for each one of these 5 edges, I can have a representation where one of the literal is going to be an x. So with this, what our job now becomes, we started out with 5 midterms, and I had to OR all the 5 midterms. Now my strategy is going to be, I'm going to select edges, and I'm going to select enough of these pink edges so that all the vertices that I'm interested in are covered. That is, one of those pink edge should cover, one of the pink edges does cover each one of our 5 cyan vertices. So looking at this, how many edges do you think I need? How many edges or vertices total I need to cover all the 5 windows? So minimum number of edges and vertices that I need to cover all the 5 cyan colored vertices. Anyone wants to shot? 3? Yeah, 3 is correct. So let's see why is 3 correct. So looking at this, if I start out with this vertex, it has it's only on one edge. So I have to take this edge, 0, 1x. But when I take this edge 0, 1x, then 0, 1, 1 is also included. So the AND gate corresponding to this back edge covers 2 of the vertices. Now I have 3 remaining vertices, and I could cover them, for example, using this top edge and this front vertical edge. And those 3 edges are going to cover all the 5 vertices and thereby cover all the midterms, because any of the midterms being 1 corresponds to one of those edges being 1. So let's see how it kind of plays out. Okay. If I were to just simply do it in terms of edges, then I am going to write it as the edge number 0, 1x, or edge x0, 1, or edge 1x1. So I could certainly write my function in terms of these edges. So now my function is sum of edges, and in this case we were lucky that every midterm was on one of the edges. It could be that I had a midterm which was totally isolated. Like for example, let's imagine a function where this midterm 1, 0, 0, sorry, not a good example. It won't work out here. But it may be possible in some function that there is an isolated vertex. It cannot be on an edge. Then you will have to include a midterm. But here, by including these three edges, 0, 1x, x0, 1, and 1x1, which again correspond to, so 0, 1x, 0, 1x corresponds to this edge, x0, 1 corresponds to this edge, and 1x1 corresponds to this edge. And with these three edges, I am including all my five original minterms. And therefore, if I were to implement my function with this logic, which basically says I have an AND gate which takes input C and input B, a second AND gate which takes inputs B and A, B being inverted and here C was inverted, and finally an AND gate which takes input C and A, and then I OR them together, then the function I will get would behave exactly the same way as my original function where I had 5 minterms. So originally my function had 5 minterms, which meant I needed 5 AND gates of 3 inputs, and I needed an OR gate with 5 inputs. Now my function can be implemented using 3 AND gates with 2 inputs and an OR gate with 3 inputs. So I have smaller gates, I have fewer gates. So I overall kind of went out in this particular case. So merging helps. Now the same concept of merging, edges for merging nodes which differed in one variable. I could also merge larger groups of nodes where more than one bit position is being changed. So if I look at a face, so of a cube. So in this case, if I look at this face, which is 101, 111, 011, and 001, what literals are changing and what are being held constant? So if I take that set of those 4 vertices, is there any literal which is remaining constant? A equal to 1, right? What about, am I covering all possible combinations of B and C? There are 4 possible combinations. All of them are being covered, right? 0, 1, 0, 0, 0. All 4 of them are being covered. So across that face, what's happening is that I don't care about values of B and C because all of them are occurring, but A must be 1. So this face could be written as, and I think I'll just switch to the next slide. This face could be thought of as xx1, right? This face corresponds to B I don't care, C I don't care, but A should be 1. And then of course the whole cube is xxx, right? I don't care about any one of them. Okay, it's always so face could be written as xx1, and in this nicely behaved function, I could indeed create a face. So now my strategy would be, I'm going to start with this cube, I'm going to put the vertices, and I'm going to start clustering the midterms, those vertices where the function had a 1 value. I'm going to start clustering them together into as large clusters as possible. Clusters would be powers of 2, so there will be either an edge or a face or in a higher dimension a cube or hypercube and so on and so forth. So in this particular case, I could cluster things into a face. So now to do what we started out to do, we want to cover all the midterms, all the vertices with that sine cube, but I want to use as efficient logic as possible, which means as large a cluster as possible. I would pick a face instead of edges. I would pick edges instead of midterms. So in this particular case, if you notice, if I pick this face, xx1, and I pick this edge, 0, 1x, then I would have covered all the 5 vertices, right? I mean, the face covers these 4 vertices, and this edge 0, 1x covers these 2 vertices, and the vertex, this vertex at the back right, 0, 1, 1, is being covered both by the edge and by the face. That's fine. All that means is both the AND gates are going to output a 1, and that's fine with us. So our function now becomes this face ORed with this edge, and that's what we see out here. It's xx1, which is our face, and 0, 1x, which is this edge at the bottom back. And that can now be written as the function xx1 is A, and 0, 1x is C bar B, so not C and B, and again A doesn't matter. So this is my function, A or not C and B. So now what I need to implement this, I started out with 5 3-input AND gates and a 5-input OR gate. Now I have been reduced to 1 2-input OR gate and 1 2-input AND gate. Okay, so I've significantly reduced the number of gates that I have that I need to realize this function. So what seemed starting out very complicated now suddenly is a very simple looking function, A or not C and B. Now in this example, doing by hand, we could see how this clustering is done. Now let's imagine you are trying to do it with a function which has 50 inputs. So you are dealing with 50 dimensions, and now you have to find all this covering. And not only do you have to worry about faces, but you will also have to may have cubes, and you may have 4-dimensional cubes and 5-dimensional cubes, all the way to the 49-dimensional cubes that you have to worry about. Computationally extremely challenging, and in fact, algorithms to do this, these are what in computer science are called as problems which are intractable. That is, to solve them, to really find the best solution, you basically have to search through everything. So people come up with what are called as heuristics or strategies which most of the time give a good enough solution. So a lot of work, even to this date, kind of goes into coming up with better and better ways, and then better and better algorithms to solve this problem, because there's a lot of money riding on it. If you can run faster, or you can come up with a better solution than other algorithms can, then it results in cheaper chips, and sort of, Intel makes more money, or other companies make more money. So there's a lot riding on this. A lot of work happened, but kind of the early stuff happened in like late 80s, early 90s, and kind of pretty decent tools emerged. So last time I said, you don't do this stuff by hand. You don't do this stuff by hand because even though I mean, as humans we are pretty smart, but this kind of drudge work computers do very, very well. So in most cases, other than some trivially for trivially small stuff, computers do pretty well anyway. And for complicated stuff, we don't even stand a chance of coming up anywhere close to computers. So, bad news for you is that in this course, you still have to do stuff by hand, just to kind of learn the concepts. But this is what kind of goes under the hood. Now, what we'll see shortly is that as humans, we don't like to think in terms of these multi-dimensional stuff. Computers are very good at it, but we are not. So what happened is that people came up with stylized ways of representing these cubes in a 2-dimensional array form. And it's something called Carnot maps. We're going to look into that. That's how, when you are doing hand optimization, you're going to kind of work with that. But computers use these cube representations internally to optimize Boolean logic. So let's see if before I kind of move on, I just wanted to kind of, let's say I am looking at this edge. What would be the label for this edge? So the one which is above the origin on the left. Anyone want to take a shot? X00, correct. So the first bit, it is changing. So this edge is X00. Okay, did everyone get it? So what's happening out here is that we are going from 0, 0, 0 to 1, 0, 0. So first position we don't care. The other two positions have to be 0, 0. So it's X00. Let's look at this face, the one which is at the top. What is this face? The label for this face going to be? So it would be 1x1. Excellent. Yeah. Oh, sorry. 1, 0. This would be 1xx. I'm sorry. Okay. What about this face, the left face? So, x 0, right? A is 0, the other two dimensions are changing. So that face is going to be x 0. Okay, so the idea is that each face, each edge has a label. The whole cube has a label x. And then kind of you start out with your function, you find kind of what faces and edges and vertices will cover it. You try to first pick faces, then edges, and only then vertices. And you OR them together, and you'll get your implementation. Now, what happens if I have more dimensions? So just to kind of show how things work out in a 4-dimensional function. So this is back to our original function, 4-bit 1-or prime. So in this case, my minterms that we are interested in are 1, 2, 3, 5, 7, 11, 13. Now, to draw this 4-dimensional thing, what we have is a cube inside a cube. And the dimension which is kind of connecting the two is the D dimension. So think of our outer cube as our original ABC, but with a value of D equal to 1. And I have an inner cube which corresponds to, again, DCBA, but it has a value of D equal to 0. So for example, this vertex where my cursor is, this guy, see how its label is 0, 0, 0, 1. This guy's label, so D is 1, the remaining values are the same, so this is 1, 0, 0, 1, and so on and so forth. So this is a visual representation of a 4-dimensional cube, and my particular function, which corresponds to 1, 2, 3, 5, 7, 11, and 13, corresponds to these vertices where I have a dark circle. So you see 4 and 5 in the inner cube, and then we also have 2 in the outer cube, so which corresponds to 11 and 13. So I have a total of 7 vertices that where the function takes on the value 1. And my goal is to cover them with as large clusters as possible. So for the inner cube, we already did it. We had this edge, and we had taken this face. But for the 2 minterms on the outer cube, I can use this edge and this edge at the back out here. So with our original stuff and 2 more edges, I can represent this new function. So what would this function look like now? So so what's the best way of implementing this 4-input 1-or prime function? And again, kind of our goal is to use as large clusters as possible. So let's start with, what would you pick first? What's the largest cluster that you see? So it's the face, but what's the label? What's the label for this face? So this particular face has the label for D, it's 0, X, 1, okay? What about this edge? We have to take that edge because otherwise we will not be able to include this minterm. So what would that be? 0, 0, 1, X. Then I have to include this edge because that's the only way I can include this minterm at the top. What would be the label for this edge? X101, so that's correct. And finally, what would be the label for this edge? So, anyone wants to speak louder? x011, excellent. And so now to implement my function, I should basically take these 4 labels, which together cover all my vertices, and do it. So I have 3 edges and 1 face. The 3 edges correspond to AND gates with 3 inputs, and the face corresponds to an AND gate with 2 inputs. And I will OR them together. So what kind of gates do I need now? How many AND gates of what type do I need, and how many? And of course I need 1 OR gate, but how many inputs? So my OR gate, how many input my OR gate is? 4, because I have 4 labels. Whereas originally this function, the OR gate had 7 inputs. So I have significantly reduced that complexity. Then I need 4 AND gates. What kind of AND gates would they be? One 2 input corresponding to the face, and 3 input corresponding to 3 edges. So I need those AND gates. And originally I had 7 minterms, so there I had 7 AND gates with 4 input each. So significant cost reduction that has happened. To a very good first order approximation, the cost of a circuit is equal to you add the number of inputs across all your gates. So originally I had 7 AND gates of 4 inputs, so that's 7 times 4, 28. And I had 1 OR gate of 7 inputs, so that's 7. So I had a total of 35 inputs to the various gates. So my cost was 35. What's the cost of this revised circuit? So I have an OR gate with 4 input. I have 3 AND gates with 3 input, and I have 1 AND gate with 2 input. So any simple addition, right? So what would be the cost of the circuit? How many total inputs do I have across the gates? 15 or 14? Let's see. 3 times 3, 9 plus 2, 11. Oh, yeah, you're right, 15. So I have 15. And originally I had 35, right? That's what we calculated. So more than a 50% reduction. And that's kind of the big win that we are seeing with an approach like this. So this kind of writes down the function, which we kind of already saw. Okay. Now, all this cube business, as I'm sure you would agree, is kind of hard to draw. And also, I guess, for many of us who may not be as good at spatially visualizing multidimensional thing, it may be hard to kind of follow also. So what has happened, as I was mentioning earlier, is that people in digital design, they kind of develop stylized way of taking these 4-dimensional and even 5 or 6-dimensional things and then kind of putting it down as matrices and arrays, which are arguably kind of easier to deal with from a human perspective. So what we do is we take our 4-dimensional cube, which has 16 vertices, and we represent it as this 4 by 4 table. And the idea is that this is kind of a funny table. It is a toroidal table. What I mean by that is, if I walk right on this table, and once I reach the right edge, I'm going to come back to the left edge. And likewise, if I walk down a column, when I hit the bottom of the column, if I continue walking, I will come back at the top. Okay, so in both the dimensions, it wraps around. And the idea now is, so you see how I've labeled these things. You see BA out here, and you see how I've said 0, 0, 0, 1, 1, 1, 1, 0. What this says is that BA equal to 0, 0 corresponds to this leftmost column. BA equal to 0, 1 corresponds to the second column. BA equal to 1, 1 corresponds to this. And finally, BA equal to 1, 0 corresponds to the rightmost column. And see how there is this big dashed line with an A. This is basically saying these are the two columns where A is 1. And likewise down here you see a line with a B saying these two columns B is a 1. And that kind of stands to reason that if you see middle two column, B changes from 0 to 1, but A is held constant at 1. And likewise, if you look at these two columns, then B is 1 and A changes. And I do the same game on this side, except that using variables B and C. DC go from 0, 0, 1, 0, 1, 1, 0, 1. Oh, sorry, 0, 0, 0, 1, 1, 1, 1, 0. Those are kind of four columns that we have out here. Now, think in terms of my four-dimensional cube. In my four-dimensional cube, so if I look at this top right box, this top right box is 0, 0, 1, 0. 0, 0, 1, 0 is sitting out here at the back inside of the cube. What are the neighbors of 0, 0, 1, 0? Firstly, how many neighbors does a corner have in our four-dimensional cube? 4, right? And so if you look at out here, it has a neighbor out here. It's a neighbor out here. The other neighbor is wrap around from this. So this guy wraps around to here. So these two are neighbors. And likewise, I wrap around from here to here. So these two are neighbors also. So my neighbors, so this one is 0, 0, 1, 0. This one is 0, 1, 1, 0, which is a neighbor because changes only in one value. This one is 0, 0, 1, 1, which is also a neighbor. This guy is 0, 0, 0, 0, and that is a neighbor because it changes only in one value. And finally, the bottom one is 1, 0, 1, 0, which too is a neighbor because it only changes for value D. So neighbors in my cube are also neighbors in this grid as long as we are willing to say that neighborhood also implies wraparound. So I can wrap around from the top edge to the bottom edge, or I can wrap around from right edge to the left edge. So when we were trying to merge edges and faces, we can do the same thing here by looking at the neighborhood relationship. And you have to draw this table in this particular order. See how I went from 0, 0, 0, 1, 1, 1, 1, 0. They are not in order of their values, but rather they are designed so that only one bit changes at a time. So 0, 0 to 0, 1, only A changed. 0, 1 to 1, 1, only B changed. 1, 1 to 1, 0, only A changed. And then 1, 0 back to 0, 0, only B changed. So they are neighboring in our cube. So they are designed in a particular way. Same thing for rows. So the game that we did earlier on in terms of merging edges and faces, I can do the same kind of thing on this array, but kind of easier to draw than trying to draw that four-dimensional cube. So let's see how that kind of plays out. So I'm going to write down which board line in the map here on the table. So like this board line means for those two columns, C is 1. Okay, likewise, this board line at the bottom means for these two columns, namely the two right columns, B is 1. Okay, and likewise here and likewise here. It just makes it easier for you to kind of keep track of things. So not essential to draw, but it's a good practice to draw. Okay. So now what we'll do is we are going to fill out this table with the minterms that are supposed to be 1s or 0s. So the first one is 0, 0, 0, 0, which is minterm 0. Our function is 0 there, so we write a 0. Next one is minterm corresponds to 0, 0, 0, 1. That's minterm number 1, so it's 1. Then next one is 0, 0, 1, 1, which is minterm number 3. And you would see how I have listed down at the bottom right corner of each square which minterm it is. And we know we want minterms 1, 2, 3, 5, 7, 11, and 13. Those are our functions. So I fill it out. So this is minterm number 1. Next one, minterm number 3. That's also a 1. Minterm number 2 is a 1. Minterm number 4 is a 0. 5 is a 1, 7 is a 1, 6 is a 0, and kind of the rest are filled up. So this is another way of representing my truth table, or another way of representing that four-dimensional cube with those labeled vertices. So we fill out this Carnot map, as it is called. Now, trying to merge edges and faces becomes merging neighboring ones in this table. So, for example, let's look at these two ones out here, row 1 and 2, column 2. So these are min term number 1 and 5. They correspond, they are neighboring here, and therefore there must be an edge corresponding to them out here also, because they correspond to 0, 0, 0, 1. So let's see, so this is 0, 0, 0, 1, and then the number 5 is 0, 1, 0, 1, which is out here, and see how there is an edge corresponding to them, right? And therefore they are neighbors out here. So whenever we were merging edges, now in this table becomes merging ones which are neighboring to each other, but neighboring here also means you should be willing to wrap around. So, for example, this one and this one are neighbors because I'm wrapping around the top to bottom. And then you see this is an edge that I can merge. This is another edge I can merge. This is another edge which is mergeable. There is this edge which is mergeable. I can merge this one also. I can merge this one also, and I think I've covered all of them this way. So there are a whole bunch of possibilities of edges out here that I can combine, and they basically mean they are in neighboring, they are in the same column, neighboring rows, or same row, neighboring columns, but you should be willing to wrap around. What do faces correspond to? Anyone? So what pattern would correspond to a face? Okay, square is one possibility, 2 by 2. So we see one square out here. Okay, so this whole thing, okay, that pattern of 4 ones appearing in a square pattern, that corresponds to a face, and we do have a face out there which corresponds to that. Do you think faces may occur in some different pattern also? A line that wraps around, or actually rather all the entire row being ones.
4 edges?
4 corners. 4 corners, yeah. So those are the two patterns. So one is I can have, it doesn't occur in this example, but you can imagine I may have like an entire row, a column of 1 or an entire row of 1. So that would be a face. But the one he pointed out from the back is the most interesting one. Let's imagine that I had a 1 at this corner, a 1 at this corner, a 1 at this corner, and a 1 at this corner. They can also be combined. They also correspond to a face. Which face do they correspond to? So again, the 4 corner squares, if they had a 1, we are saying that represents a face. What face do they represent? Anyone? No? A equal to 0. Okay. So D changes because D is 1 out here and 0 out here. So D is an X. C changes because C is C is 0 here. C is No, so it A is 0 and C is 0, okay? And then B changes because B is 0 and a 1 out here and A is 0 out here, okay? So you basically keep track of what is changing. So in this case, B is changing and D is changing and the other two are being held constant. So the four corners would correspond to the face X, 0, X, 0, okay? So faces therefore occur in four distinct ways: a 2 by 2 square, 1 by 4 thing, a 4 by 1 stuff, or 4 corners. And the 2 by 2 square can also occur in this way. So let's imagine I may have, let's say, a 1 here, in 9 and 11, I have two ones here. I can have, because of the wraparound property, my square may be split across the wraparound. So that also can happen in the Carnot map, but it would still be a 2 by 2 pattern. So the idea is manually you'll have to look for these patterns, look for faces, look for edges, and once you have done that, then you are basically going to find what is the minimum number of faces and edges and standalone boxes do I need to take care of all the ones which occur in the function. That's kind of going to be the strategy. Exactly what we did for cubes, but we are just doing it in terms of these tables. So we'll go through more examples to kind of practice this a bit. So positions of minterms on the Carnot maps, they basically correspond to what were in faded letters earlier on. Adjacent minterms are different only in one bit, so we saw that property. So like if I take any two of these, like if I look at this guy and this guy, they differ in one bit only. If I look at like this corner guy, this one, and let's say this one, they are adjacent and they only differ in, sorry, not this. If I look at this and this, then they differ in only one bit, and so forth. So you can always kind of wrap around and still be adjacent. So Carnot map of 4-bit primes that we had done, it was 1 OR prime. So 1, 2, 3, 5, 7, 11, 13. So the red ones are the ones which we want to, where our function takes on the value 1. And now we are represent them by corresponding minterms. We combine them. So one possible way of combining them is like this. I combined these two boxes here, I combined these two boxes out here, and I have left with these three standalone. So that could be one way of doing it, but we can do better because we have a face here. But idea is you combine edges and minterms. You can also combine these two, so edges wrap around. So we've gone over this one. We can combine a face, so you see this face, 0xx1. So you draw this Carnot map, fill it out with ones and zeros, and you kind of start combining stuff. First see, is there a face? Then once you have taken care of the face, see what are the edges. And then hopefully you are not left with any standalone individual boxes. That would be your goal, but sometimes you will be forced to. So before we go into more examples, this kind of strategy leads to time for some more definitions. So we saw minterm earlier on. Minterm is an AND term or a product term where each input of a circuit or its complement is present. So if a circuit has 5 inputs, then my minterm will have 5 terms. They will be ANDed together. Some of the terms may have a complement on them. So we already saw that before. Implicant is a product term. That implicant of a function is a product term, which if it is true, then a function is true. So implicant is an expression of the form where some of the inputs are ANDed together, but not necessarily all of them. And the property is that an expression is an implicant of a function if whenever that AND expression is true, the function is true. So an edge is an implicant, a face is an implicant, when you kind of merge things in the Carnot map, when you merge neighboring blocks. Prime implicant. Prime implicant is an implicant that cannot be made any larger. That is, it's an edge which is not part of a face, or it's a vertex which cannot be merged into any of the edges. None of them, a vertex where none of the neighboring vertices are one would be a standalone vertex. So that would be a prime implicant. So anything which cannot be made any larger is called a prime implicant. Essential prime implicant means that there is a vertex and only this implicant covers that vertex. Only this prime implicant covers that vertex. So there is no other way that vertex could be covered. So let's take an example. Let's say I have three variables x, y, and z. If xz is an implicant, then xz being an implicant means I don't care about y, which basically means that 101 and 111 are covered by xz. If x is an implicant, then that means that this x covers 100, 101, 110, 111. All the other combinations of y and z are possible. Implicant x is larger than implicant xy because x covers more vertices than, or more cells in my Carnot map than xy does. So if we go back to our Carnot map for a moment, this one. So let's look at this face, one corresponding to 1111. It cannot be made any larger, so it's prime implicant. Or for example, if I look at this edge, which would combine cell number 3 and cell number 2, is that a prime implicant? Can it be made larger? Can that edge be made part of a face? No, because I have a 0 here, I have a 0 out here. So this edge, which is linking 2 and 3, is a standalone edge. It actually is this edge at the back out here, and you can see it's not part of any face. So that too is a prime implicant. This one. It too is a prime implicant. Moreover, it's an essential prime implicant. What I mean by that is that that's the only prime implicant which covers the cell number 2. Because cell number 2 is hanging out by itself, and only this edge covers it. On the other hand, there might be cases where it doesn't occur in this example. It might be a case that some vertex could be covered by 2 different edges, and I have a choice there. But that's not the case in this particular example. So going back to our definitions then, min term we saw earlier on. Min term is an AND term which has every input present in it, and the function is 1 for that min term. Implicant is a product term where function is 1, but not all inputs are necessarily present in that AND term. So a face and edge, these are implicants. A prime implicant is if it cannot be made any larger. So if an edge could be part of a face also, then that edge is not a prime implicant. An essential prime implicant is one where that's the only prime implicant which takes care of a vertex. The reason it's called essential is because in any implementation of the function, you should include that prime implicant because that's the only way you are going to cover one of the midterms. So let's see this thing in action. What my goal then is, as we've been intuitively talking about, we want to cover all the. Okay, so min term, in min term, the AND term should include all my inputs that are in the function. So if my function has, let's say, input A, B, C, D, then min term has to have an NP for A, an NP for B, an NP for C, and an NP for D. They may be complemented, but all 4 should example, A, not B, C, D, that's a minterm for the 4-bit, 4 input function. On the other hand, an implicant is one where not all entries need to be present. For example, A and B is an implicant, but because it's not including C and D, so therefore it's not a minterm. Okay, and so as you can imagine, implicant are obtained by merging things. So an edge would not have one of the inputs present. A face will not have two of the inputs present. So they are implicants. They are not minterms. Yeah? Right.
So you're saying that implicants are the ones that make the function true, but minterms is just all the possible.
Okay, so let's take. We'll just write it down here only. Okay. So let's say I have a function which takes 4 inputs, A, B, C, and D. Okay. And let's say the function is true for A, B bar, C, D. And let's say the function is also true for A, B, C, D. Both of these are minterms. I could also combine these two minterms and write A, C, D. And that's an implicant. It's implicant because B is not occurring out here, but the function is true for ACD also. Okay. Of course, minterm is also an implicant, but not all implicants are minterms. Okay, and then prime implicant means that I cannot shrink this thing anymore. Okay, so it cannot be made part of something even smaller. Okay, so going back to our covering story, then the red boxes indicate the minterms where our prime function has an output of true, and we want to cover these things. So strategy is always start by the largest possible things. In a 4-bit function, 4-input function, you'll have to start by looking at faces. So we see a face here, or kind of this 2x2 square. So I label that, and that would be 0xx1 because D is 0 here, and A is 1 out here. The other two variables are changing. So this square represents a face in our cube terminology, and it corresponds to 0xx1. Once we have taken care of the face, is there any other face on this one? When we have been following this example, there is none because there is no other pattern. There is no 2x2 pattern, there is no 1x4 pattern, there is no 4x1 pattern, and there is none of those corner patterns. So faces we are done. Then we start looking at edges. So our goal is now we have to try to find edges which cover cells which have not already been covered, right? I mean, our goal is to now sort of do that. So what we'll do is we can take this edge, it covers 2, and that edge is 0, 0, 1x because A is changing, the other 3 are constant. I can take this edge, and then finally I can just take green edge, which is a wraparound type edge. So I introduced 3 edges, and with those 3 edges, I have now covered everything which was supposed to be 1. So I need a face and 3 edges, which is what we had in our cube also. I don't need any standalone minterms, so my function is nothing but just an ORing of these 4 implicants. So each one of these 4 are prime implicants because they cannot be grown larger. Each one of these 4 are also essential implicants in this case because let's take the blue one. The only way this cell 1 can be covered is through this prime implicant, the face. Likewise, 13 can only be covered by this, 2 can only be covered by this, and 11 can only be covered by this green one. So they're all they're all implicants, they're all prime implicants, and in this particular example, they are also all essential prime implicants. And your best, your goal basically is to try to come up with the set of prime, fewest prime implicants to represent the function, which would be the most efficient covering question. It doesn't, but what it means is that if a midterm can be covered by multiple faces and edges, then that means that it's possible that those things are not essential. Now, in this case, it doesn't happen because there's always some midterm which is only being covered by one option.
So if it's 3 in a row, then the one in the middle wouldn't be considered essential, right?
If I had created an X called 1, 3, let's say, okay, well, 1, 3 is not even a prime implicant, right? Because 1, 3 is part of my face. Okay, so it's not even a prime implicant, let alone one more. So in this example, unfortunately, there is no non-essential prime implicant in this particular case. Any other questions? Okay, I have another example we'll go through later, or if I don't come through, then the TAs would. So the intuition is that we want to create large implicants because large implicants mean smaller gates, and we basically want to go after the essential prime implicants first. So we'll kind of see. There are times on where you may deliberately go for a less efficient solution. And towards the end of this module, we are going to talk about why that may be. It has to do with some erroneous behavior that real-life circuits may exhibit, and dangerous behaviors, which sometimes require that you kind of back off and include some extra terms in your implementation. And we'll talk about it, something called hazards, but right now, so once we have our cover, this kind of minimal efficient covering of all our midterms, then we can basically map things to gates. So we had these 4 entries. Again, if you recall out 0xx1, 001x, x101, x011, those are the 4 entries. And we can map them to gates like this. And we discussed that earlier, that this implementation has a total cost of 15. So cost equal to 15, and the reason the way cost is 15 is I have a cost of 3 here because 3 inputs. I have a cost of 3 for this gate also, a cost of 3 for this gate also, a cost of 2 for this AND gate, and a cost of 4 out here. So this is 3 plus 3 plus 2 plus 4. Okay, so that's how we do the cost. And when we had started out, I had 7 midterms of 4 each, so that was 28, and then I had an OR gate with 7 inputs, so total of 35. So original cost before we did all this stuff was original cost was 7 times 4 plus 7, which was 35. Optimized cost is 15. So huge win. It would be a smaller design. It would actually be a faster design, and it would consume less power. So you gain in every which dimension out here. And some kind of real life issues. So when we drew it, we have these AND gates with bubbles at the input. There are no such real life gates. There are no AND gates with built-in inverters in the input. So in reality, the way you would implement it is to have to put inverters for them. The other thing is that this structure of AND and OR is not very efficient. So what is often done is to optimize this thing. So the reason is in our technologies, the basic gate that you can implement very efficiently are NAND and NOR. NOR happens to be faster than NAND, but so if you need an AND gate or if you need an OR gate, you have to put an inverter in front of it. So to create this AND gate, so firstly, these input bubbles, we have to put our inverters out here. Then we are left with AND gates. But as I'm saying, there are no AND gates. There are NAND gates, and then we put an inverter in front of it. So we do that. So we replace this AND gate by a NAND gate. So we put a bubble out here, but then I have to put two bubbles, otherwise the logic will invert. So I also put bubbles at the input of this OR gate. So again, what's happening is each one of these input bubbles I replaced by inverter. And then I converted these AND gates to NAND gates, but then put an additional bubble at the input of the OR gate. So now I have NAND gates out here, but now I have this OR gate where the inputs are all bubbled. What is this gate? An OR gate with all the inputs inverted. Last time we had talked about it. So what does this correspond to? Our favorite theorem, De Morgan's theorem, what does that say? So yeah, you were saying, someone was saying, NAND gate, OR gate, NOR gate. Huh? Well, so what De Morgan said was that, or the duality theorem said was that if I take the dual of a function, apply it to inverted version of all the inputs, then it's the same as our function inverted. Okay? So OR gate with inputs inverted is the same as an AND gate with the output inverted. Right? So which is another thing is an OR gate with input inverted is nothing but a NAND gate. So what this guy out here is actually a NAND gate. So our sum of products becomes NAND followed by NAND. And that's how, in actual transistors and all, that's how it will get implemented. If you had product of sums, which we'll also see, the product of sums becomes NOR followed by NOR. But again, because of this. So being able to kind of move back and forth between kind of logic in this way is very important. So you need to be very comfortable with the transformation implied by De Morgan's theorem. Quite important to do that. Okay, so earlier on we had talked about that how sometimes we may have functions where for some of the inputs I may not care what the function is. So we had that example with thermostat where the setting, set temperature was only 3 out of 4 2-bit values were specified, so we didn't care about what happened instead. Let's imagine we are doing the same thing out here, except, so again we are doing our favorite one or prime function, except that I tell you that the input will never be more than 9, so that the input would be 0 to 9, it's a decimal input, and that values corresponding to 10 through 15 in the 4-bit one will never occur. So in that particular case, these final entries of my truth table are don't cares. We just put it as X or D or dash, so something like that. But that is to indicate that I don't care what the circuit will output when the input is one of these values, because we guarantee you that that input will never occur, or even if it occurs, we don't care about what the output is. So what another way of saying is that for these rows, depending upon what is convenient, you can pick the output to be 0 or 1 for each one of them separately. You don't care what it is. So in our Carnot map terms, so first in notationally what it means is that min terms 1, 2, 3, 5, 7 are required. That's when the function is 1. But then the other ones, 10, 11, 12, 13, 14, 15, they are part of a don't care set. They could be 1 or 0. I don't care which one. Pick whatever you're comfortable with. So in our Carnot map, what happens now is, for those terms, in our case 10 to 15, we're going to put an x. X indicates that you can think of it as 0 or 1, either one. But you have to make a choice for each cell individually, but you could pick whichever you want. So what strategy would you use? How would you, what should drive my process for selecting zeros or 1 for these x's? To make large clusters. Excellent. So remember, our goal is to combine things into faces. So I will pick those values of x's which will result in more and more faces and more edges, right? So that I end up having a better implementation. So looking at this, could you suggest what might, looking at this, obviously one face sticks out. I mean, there is a face out here that is already, that is there, so that's great. And if I were to implement with this, I'll have a face and I will have a singleton 1. That would be my normal implementation, right? I mean, if I were to think of all x's to be zeros, then I would have a face. Sorry, I take it wrong. I will do this and I'll do an edge like this, right? That would be my implementation. One face, one edge. What could you do better? By judiciously selecting some of the x's to be 1s and the rest 0, could you give me a better implementation than one face, one edge? For example, I cannot make anything bigger than a face easily, but I can make a cube if it's possible, or I can turn my edge into a face. So is there a way to turn that edge into a face? Yeah, so I can make these two guys to be 1s, and then I will have a face like this, right? So if I select these bottom two 1s to be 1s, then I end up with a face. So instead of an edge, which would have 3 inputs and gate, I will now have a 2 input and gate. So save a little bit of cost. Is there a way to turn any of the faces into a 3D cube? Not in this example, so. But generally speaking, you can kind of do a larger and larger clustering if possible. So this is one. This is another prime implicant. I could have picked this one also, but it's not essential. This one, which was suggested. There is this possibility also. I can select those two x's to be 1s. And that's what we kind of end up with. So these are all our prime implicants. Now what we need to do is we need to find prime implicants which are essential. So which ones are essential? So I have a blue colored or a cyan colored one out here, 0xx1. I have this purple color xx11. I have this brown color x1x1. And then I have x01x, which is this green colored one. So question number 1, are there any prime implicants here which are essential? That is, they are the only one covering a midterm. Okay, you have answered enough. Someone else wants to answer? Any prime implicant, namely these groupings of 4, where they are the only one covering one of the cells. One answer? Well,
X1, X1.
huh?
X1, X1.
X1, X1. Uh, okay, so you're saying x1 is an essential prime implicate. Okay, so that's another way of saying that that's the only one covering some cells, but that's not true, right? I mean, it's covering these two cells, 1 and 1, but they're also covered by the blue one, so it's not essential. 0xx1. Okay, so that's the sign colored one, and that one is essential because this top left, this one out here in box number 1, that's the only, it's being only covered by that. So this certainly is essential. Is there is there anything else essential? X01X, so that's the green one, and that's essential because that's the only one which is covering this top right. So this is essential. So first thing you do after you form those big cluster, find the essential ones. Those I need. So I need the 0xx1 and I need x01x. Once I have picked these two, are any of the ones uncovered? So are there any remaining min terms which have not been covered by these two choices? They're all covered, right? I mean, anything left over is either an x or a 0. So in this example, these two essential midterms are sufficient. In some other case examples, depending upon the function, it may be that you may have to pick some additional terms also. So the strategy is first start with essential ones because you know you're going to need it. And once you have picked all the essentials, then see whatever is left uncovered, and then now the hard part begins. You have to find what's the best combination. So our function in this case can be implemented as 0xx1 or x01x, which basically means 1 2-input OR gate and 2 2-input AND gates. So we picked the essential ones. We just kind of went through this. These two are the essential ones. And with these, I have covered all the min terms, all the boxes where there was a 1, and I'm done. Remaining values of x's, we are basically treating them as zeros, and we are done with that. So our implementation in terms of gates would look like this. And I can, instead of writing it as OR and AND, we always like to write it as NAND followed by NAND because that's how we implement it. Okay, so that was sum of products. And since everything is dual in nature, so we also have product of sums. And the dual, instead of using minterm, we use maxterm. So the idea is that in sum of products, which we were doing thus far, we were focusing on whichever entries were 1 in the truth table. Now we are going to focus on entries which are 0. And this is the counterpart. We are going to teach it to you, but it's less commonly used in manual analysis. Most of the time people just do sum of products. But it's good to know, and in fact, in modern technology, if one were to do it, it's probably better to do product of sums just in terms of the speed of gates and all. But again, we don't do it by hand, so all of that is of academic interest. But I'm going to walk you through it, that how product of sums work. So what we now do is, we take our truth table, and we are going to focus on wherever we are going to focus on things where the function is 0. So what we have is a function f which is 0 when DCBA is 0. So that's this guy. Let's see what happened. Okay, so I have I think my description here is messed up. I have a truth table like this, and what we have is these two entries which are 0, and basically what my function is now going to look like is the max term corresponding to these two rows, and which, if you recall, the lowest one is max term number 0, and this one is max term number 2. We count from the bottom. So our function in this form looks like the ending of these two max term number 0 and max term number 2. So the basic idea is that if, for example, DCBA is 1, 1, 1, 1, then that's when we want the function to be 0. So that particular term would be 0, and the output of the AND term would be 0. So let's see how it kind of plays out. So in the Karnaugh map for these kind of functions, what we do is we focus on where the function has 0 values. So in this particular case, the 0 values are in these two boxes, box number 13 and 15 in our previous truth table. And the same game that we were doing earlier on, where we were clustering ones, now for max term implementations, we want to cluster zeros into edges, into faces, into 3D cubes, and so on and so forth. So in this case, I have these two things, and I'm going to cluster them together, and I'm going to OR them together. So when you cluster these things together, they would become 0, 0, x 0. You OR them together, you end up these three entries. So that's my max term, and my function is represented by this. So it's a counterpart of just a dual of what we were doing earlier. With the ones we were ANDing things. Here we are ORing things, and then different implicants or prime implicants, we were combining them using an AND gate. Here you will combine them. There we were combining them with OR gate. Here we'll combine them with AND gate. I'll go through a more detailed example, but kind of very sketchy fashion. The way you deal with these max terms is to focus on zeros, merge them, apply the same technique. Wherever we had OR, we had AND now, and vice versa. Okay, so let's look at this example, decimal, prime, or 1. So we saw it a short while ago. So I have 0 here, 0 here, 0 here, and these two zeros. So 6, 7, 9, 11, and 15, these are the places where I have zeros occurring. And then I have a bunch of don't care set. So now what I'll do is I'm going to make some of my don't cares to be 0 so that I can cluster zeros more efficiently. Previously, we were making some of the x's to be 1 so that I could make big clusters of 1. Now my goal is to make big clusters of zeros. So looking at this, what x's can you make to be 0 to get a big cluster of zeros? Yeah, excellent. So I do all of them, and then I cluster them into what? What does it become? So the suggestion out here is, let's make all these x's to be 0. And indeed, that's correct. I get this 2 by 4 cluster out here of zeros. What does that cluster correspond to? What's the label of that cluster? Or in our cube terminology, what does it correspond to? Anyone? Don't be afraid to speak. Yeah, it's a cube. Yeah, it's a cube, 3D cube in our 4D space. Okay, and specifically, this is a cube corresponding to where C is changing its value, A and B are changing their value, so it corresponds to D equal to 1. Okay, so that's the cube out here. So in this case, as you can see, by treating all those x's as 0, I end up with a very efficient implementation. So I have one big stuff that covers these two zeros. I also have this vertical one, which would cover these two zeros. So I will have a face, which will cover it. And then I'll have to kind of take care of this 0 as part of another face. I can take this 0 out here, the x out here, this 0, this x, I have another face. So 2 face and a cube, 2 face and a 3D cube is going to cover this function. So that's how I'm going to cluster them out. So now what it becomes is, for a given function, you may see that if I try to cover 1, it may be better, or maybe it may be better if I try to cover 0. It depends on the function. Some functions are cheaper to implement with sum of product. some other functions may be cheaper to implement as product of sums. It depends upon how zeros and ones are distributed in this kind of map structure.
So in that example, can't you just implement it with minterms and then just like invert the answers?
You could do in minterm. Yeah, we'll come to these strategies a little bit later. But you certainly, for first thing, any function you can do with minterms also. So that's just a choice you make. I'm just kind of showing out here. If I were to do it with merging zeros, this is kind of the process I would follow. But certainly we could do it with minterms also. And the other thing you can do is you can invert the function, do it minterm, and then invert. That's a great way to do it. But then in that case, it is not sum of product of sum, it's rather invert of a sum of product. But nothing wrong with it. So I guess in a exhaustive sense of design, one has to try out all of these. Luxury of having computer programs doing it is that they do it for us. So as designers, one would not have to worry about it. But obviously, some very smart people came up with those algorithms to kind of solve these kind of problems efficiently. That's out there. So this is, and then this face and this face, they together cover everything. And we basically end up with an implementation that looks like this. Now what you see out here is that my max terms correspond to the OR gate and they are ANDed together. So this is product of sums. Sums are the OR gates and the product out here. So again, these are the three things, the OR term here, the OR term here, and the OR term out here. And we are going to AND them together. And we play the same game of placing bubbles out here to correspond to how things are in the technology. So it's an exact analog. Now there exists an alternative strategy which was kind of being hinted for product of sum. So what we do is we take f, our function, we do not of f. And then what we do is we do a sum of product of the not of f. Sum of product is a minterm based strategy. And then we do implementation of that. Then we take complement, and then we do De Morgan's theorem to get product of sum. So the strategy here is, let's say you are uncomfortable with thinking about max terms and all. So given a function, you take its invert. So wherever you had ones, they become zero. Wherever there were zeros, becomes ones. Wherever there was x, remains x. Now you have a new Carnot map corresponding to the invert of the function, complement of the function. Now you apply your minterm strategy, cluster ones together, come up with the implementation. Now you have an implementation of complement of f. Now, since you wanted f, you place an inverter in the front, and then you kind of go back with our duality theorem and come up with product of sums. So let's take another example. So we are back to product of sums. So this is our Carnot map, and we want to create a product of sum version of this. So strategy one is we focus on where the function is zero, and we merge them. So this is kind of the normal strategy that we follow. How are we on time? Okay, a few minutes. So what I could do is I can form these two neighboring clusters. So these two zeros get combined, these two zeros get combined. I have OR of 0x0 out here. And by the way, one thing you would notice is that the terms out here are complement of whatever is listed out here. So like, for example, for this edge, D is 1 according to this, but we have putting down a 0 out here because it's a max term. C is changing, so that's an X. And then BA was 0, 1, but we are putting it as 1, 0. So it's an OR of the opposite of whatever appears out here. Likewise, this thing corresponds to OR of 0, 0, X0. And then my implementation is implementation is to take these two ORs. Wherever I have a 0, I put a complement, and then I AND them together. So this is kind of the direct strategy. I personally find it less convenient to deal with because I guess I grew up learning about sum of products first, so I find that more convenient. But this is the strategy that kind of one could follow. So again, you focus on zeros, you merge zeros, you create OR terms corresponding to them, or rather max terms corresponding to them, and then you AND them together. Strategy two, and then I can convert them into gates. That mapping we know very well. But strategy 2, which I find more convenient, is that I first take my Karnaugh map, invert it. So now my Karnaugh map becomes this: 0, 0, 0, 0, and then 1, 1, 1, 1. And now I focus on the 1 entries. So I merge this. I get my min term. I get my product term. I merge these. I get another product term. I do a sum of product, but this is for the invert function. And then what I do is I apply, take this function, I transform it using De Morgan's theorem into this. So now I have product of sums. And this is exactly the same thing that we had previously, so they're equivalent. Mentally, I find the second approach, invert the Karnaugh map, do the sum of product, and then apply De Morgan, somewhat easier for me, but the first approach is exactly equivalent. Okay, so let's do an exercise. Express the three input function f M17. So it's a function where min term number 1 and min term number 7 result in logic 1 as a minimal product of sums expression. So that's what we want to do. So help me out. What would the Karnaugh map look like? So first step, you fill out the Karnaugh map. So one thing you'll notice out here is that my Karnaugh map is now only 3 variables. So on the vertical side, I only have to worry about C. Which boxes are ones? So M of 1 is this guy. And 7 would be 1, 1, 1. So this guy. Right? Yeah. And the rest are 0. So we fill that out. And again, we wanted product of sums. So we could either do strategy 1 or strategy 2. So let's do strategy 1. I combine the zeros. So there's a possible phase structure out here. That results in xx0. I can combine these. I can 0, 1x. I can combine these. That's another one. And that's all I need. All those 3 I would need. And there's nothing else needed. So I'm kind of these 3 terms would work together. And now you can kind of, depending upon which strategy you're using, you can either kind of directly go into max term, or you can first create the complement, min term for the complement, sum of products for the complement, and kind of work out from that. So I would urge you to kind of try it out on your own. The TAs, I'm going to stop at this point, but TAs will go through some additional examples from back of the book.